Download this code from codegive.com, link in the description below. Long live byte buffers, a deep dive into efficient memory management for Java I/O. Byte buffers are fundamental to efficient I/O operations in Java. They provide a direct way to interact with memory buffers, allowing for high-performance data transfer between different sources and destinations, such as files, network sockets, and other hardware devices. Understanding and utilizing byte buffers effectively is crucial for building robust and performant applications. This tutorial will explore byte buffers in detail, covering their types, creation, usage, advanced features, and best practices. 1. What are byte buffers? At their core, byte buffers are containers for primitive byte values. They wrap a primitive byte array and offer methods for reading, writing, and manipulating data within that array. The key advantage of byte buffers lies in their flexibility and efficient memory management. They avoid the overhead of creating new objects for each byte written or read, which is common when using streams directly. Key characteristics **** buffer *** a contiguous block of memory used for temporary storage of data. ***bytes *** the fundamental unit of data stored in a byte buffer. ** direct memory access ** byte buffers, especially direct byte buffers, can directly access system memory, bypassing the Java heap for even faster I/O. * position, limit, and capacity * these three attributes are vital for understanding how byte buffers work. * capacity * the total size of the buffer, the underlying byte array. This is fixed when the buffer is created. * position * the index of the next byte to be read or written. It moves as you perform read/write operations. *limit * the index of the first byte that should not be read or written. Think of it as the end of the active data region within the buffer. *flexibility * byte buffers can be configured for reading, writing, or both, read-write. *memory efficiency * reduced object creation overhead compared to traditional stream-based I/O. *thread safety, usually byte buffer instances themselves are generally not thread safe. Concurrent access requires careful synchronization. 2. Types of byte buffers. Java provides two main types of byte buffers. *heap byte buffer * this is the most common type. It allocates the underlying byte array in the Java heap, just like any other Java object. Heap byte buffers are easier to use, but data transfer between the Java heap and native I/O operations can introduce overhead due to copying. *direct byte buffer * this type allocates the byte array directly in system memory, outside the Java heap. Direct byte buffers are significantly faster for I/O operations, as data can be accessed directly by native code without the need for copying. However, direct byte buffers are typically more expensive to allocate and deallocate. Their lifetime is tied to the garbage collector, but their memory may not be released immediately. Choosing between heap byte buffer and direct byte buffer ***. Use direct byte buffer ***. When dealing with large amounts of data and high-performance I/O is critical. * when interacting with native libraries that expect data in native memory. * for network I/O where minimal latency is required. Use heap byte buffer ***. When dealing with smaller amounts of data. * when ease of use and garbage collection predictability are prioritized. * when interacting with legacy APIs that expect byte arrays. 3. Creating byte buffers. You can create byte buffers using the byte buffer class and its static factory methods. Explanation ***. Byte buffer.allocate, capacity, creates a new heap byte buffer with the specified capacity in bytes. the position is initialized to 0, and the limit is set to the capacity. Byte buffer. Allocate direct capacity creates a new direct byte buffer with the specified capacity. Similar initial state to allocate. Byte buffer. Wrap byte creates a heap byte buffer that wraps the given byte array. Changes to the byte buffer will also affect the underlying array, and vice versa. The position is initialized to 0, and the limit is set to the length of the array. Byte buffer. As read-only buffer, creates a new read-only byte buffer that shares the same underlying data as the original. Any attempt to write to the read-only buffer will result in a read-only buffer exception. 4. Writing to byte buffers. You can write data to a byte buffer using various put methods. Key put methods. Put, byte B, writes a single byte to the current position. Put, byte src, writes the entire contents of the source byte array to the buffer starting at the current position. Put, byte src, int offset, int length, writes a portion of the source byte array to the buffer, starting at offset 4 length bytes. Put, int index, byte B, writes a byte at a specific index in the buffer, without changing the current position. This is an absolute put operation. Put char value, puts short value, put int value, put long value, put float value, put double value, write primitive types to the buffer in the appropriate byte order. Important note, flip. After writing to a byte buffer, you must call the flip method before reading from it. Flip does the following. 1. Sets the limit to the current position. 2. Resets the position to 0. This prepares the buffer for reading by making the written data available for reading from the beginning of the buffer. 5. Reading from byte buffers. You can read data from a byte buffer using various get methods. Key get methods. Get reads a single byte from the current position and increments the position. Get byte dst reads bytes from the buffer into the destination byte array dst. Get byte dst int offset int length reads length bytes from the buffer into the destination byte array dst, starting at offset. Get int index reads the byte at a specific index in the buffer, without changing the current position. This is an absolute get operation. Get char, gets hort, get int, get long, get float, get double, read primitive types from the buffer in the appropriate byte order. Make sure that these types were written to the buffer in the same way. Important methods. Has remaining, returns true if there are any bytes remaining to be read from the buffer, i.e., position limit. This is essential for looping through the buffer's contents. Rewind, resets the position to 0. The limit remains unchanged. This allows you to read from the beginning of the buffer again. Mark, sets the mark to the current position. This is useful for temporarily remembering the current position. Reset, sets the position to the mark value. If the mark hasn't been set, calling reset will throw an invalid mark exception. Remaining, returns the number of bytes remaining in the buffer, i.e., limit, position. Clear, resets the buffer to its initial state. Sets the position to 0 and the limit to the capacity. Does not erase the data in the buffer. It simply prepares the buffer for rewriting. 6. Byte order. Byte order, also known as NDNS, specifies the order in which the bytes of multi-byte data types, like int, short, float, double, are stored in memory. Big-endian the most significant byte, MSB, is stored first, at the lowest memory address. Little-endian the least significant byte, LSB, is stored first. Java's default byte order is big-endian. You can control the byte order of a byte buffer using the order method. When to consider byte order network protocols many network protocols define a specific byte order, usually big-endian, often referred to as network byte order. You need to ensure that your application uses the correct byte order when exchanging data with other systems over the network. File formats Some file formats may specify a particular byte order for storing multi-byte data. Cross-platform compatibility If your application needs to read and write data across different platforms with different native byte orders, you must handle byte order explicitly to ensure data integrity. 7. Views buffers. Byte buffers provide the capability to create view buffers, which are specialized buffers that provide a different view of the underlying data. These view buffers do not allocate new memory. Instead, they provide access to the data in a different format. As char buffer, creates a char buffer view of the byte buffer, allowing you to read and write characters. As short buffer, creates a short buffer view of the byte buffer, allowing you to read and write shorts. As int buffer, creates an int buffer view of the byte buffer, allowing you to read and write integers. As long buffer, creates a long buffer view of the byte buffer, allowing you to read and write longs. As float buffer, creates a float buffer view of the byte buffer, allowing you to read and write floats. As double buffer, creates a double buffer view of the byte buffer, allowing you to read and write doubles. Key points about view buffers View buffers share the same underlying data as the original byte buffer. Changes made to a view buffer are reflected in the original byte buffer, and vice versa. View buffers provide a type-safe way to access data in the byte buffer, avoiding the need for manual byte manipulation and casting. The capacity of the view buffer is determined by the capacity of the original byte buffer and the size of the data type of the view buffer. View buffers can be used to efficiently parse complex data structures stored in byte buffers. 8. Memory mapping, mapped byte buffers. Memory mapping allows you to treat a file, or a portion of a file, as if it were directly in memory. This technique can significantly improve I/O performance, especially when dealing with large files. Java's mapped byte buffer provides a way to map a file region directly into memory. Changes to the mapped byte buffer are automatically written back to the file. Explanation *. 1. Random access file and file channel *. These classes are used to access the file and create a file channel. Random access file allows reading and writing to specific locations in the file. File channel provides a way to connect to a file and perform I/O operations. 2. RAF.setLength, file size, *. This ensures that the file is at least the specified size. If the file is smaller, it is padded with zeros. 3. Channel.map, file channel.map mode.read_write, 0, file size, *. This maps the entire file into memory using the read_write mode. The arguments specify the map mode, the starting position in the file, 0, and the size of the mapped region, file size. Other modes are read_only and private. Changes are not written back to the file. 4. Buffer.force, *. This forces any pending writes to the mapped region to be written to disk. While the operating system typically flushes changes to disk periodically, calling force ensures that your data is persisted immediately. This is important for data integrity. Advantages of memory mapping ****. Performance **** memory mapping can be significantly faster than traditional file I/O, as the operating system handles the caching and buffering of file data. Data is accessed directly from memory, avoiding the need for system calls to read and write data. Large files memory mapping is particularly effective when dealing with very large files that cannot fit entirely into memory. Data sharing memory mapping can be used to share data between multiple processes, allowing them to access and modify the same file data concurrently. Limitations file size the maximum size of a mapped region may be limited by the operating system's address space. OS dependencies memory mapping behavior can vary slightly across different operating systems. Data consistency when multiple processes are accessing the same mapped region, you need to implement appropriate synchronization mechanisms to ensure data consistency. 9. Best practices for using byte buffers. Choose the right buffer type. Select direct byte buffer for high performance I/O, especially with large data sets. Use heap byte buffer for smaller data sets or when ease of use is more important. Allocate appropriately. Allocate byte buffers with an appropriate size. Avoid frequent reallocations, as they can be expensive. Reuse byte buffers. If possible, reuse byte buffers to reduce memory allocation overhead. Use clear to reset the buffer for reuse. Manage position and limit. Pay close attention to the position and limit attributes. Use flip after writing and rewind, or clear before rewriting. Handle byte order. Be aware of byte order when dealing with multi-byte data types, especially when interacting with network protocols or file formats. Use force with mapped byte buffers. Call buffer.force on mapped byte buffers to ensure that changes are written to disk. Thread safety. Byte buffers themselves are generally not thread safe. Use appropriate synchronization mechanisms if multiple threads need to access the same byte buffer concurrently. Consider using java.utility concurrent.locks for fine-grained locking. Alternatively, create separate byte buffers for each thread. Release direct byte buffers. While the garbage collector eventually reclaims the memory used by direct byte buffers, it can take some time. Consider using techniques like Sunday Miscellaneous Cleaner, although it's generally discouraged due to its reliance on internal APIs, or using a buffering strategy that reuses direct buffers. Profile and optimize. Profile your application to identify any byte buffer related performance bottlenecks. Use appropriate optimization techniques to improve I/O performance. Use buffer pool. For network I/O, consider using a buffer pool to pre-allocate a set of direct byte buffers and reuse them for incoming and outgoing data. This can significantly reduce the overhead of buffer allocation and deal location. 10. Code example, network I/O with byte buffers. This example demonstrates using byte buffers for simple network communication, echo server and client. This example is intentionally basic to illustrate the use of byte buffers. More robust network applications should use NIO channels and selectors. To run *. 1. Compile both server.java and client.java. 2. Start the server application. 3. Start the client application. 4. Enter messages in the client console. The server will echo them back. 5. Type exit in the client console to disconnect. Explanation ***. Server ***. Opens a server socket channel to listen for incoming connections. Accepts connections using server socket channel.accept. Reads data from the client using client channel.read, buffer. Asterisk echoes the data back to the client using client channel.write, buffer. Asterisk client asterisk. Asterisk opens a socket channel and connects to the server. Asterisk reads messages from the console. Asterisk sends messages to the server using socket channel.write, buffer. Asterisk receives echoed messages from the server using socket channel.read, buffer. This example illustrates how byte buffers are used in conjunction with NIO, new I/O, channels for efficient network communication. 11. Alternatives to byte buffers, where applicable. While byte buffers are highly efficient for many I/O scenarios, consider these alternatives depending on the specific use case. Asterisk input stream / output stream asterisk for simple text-based I/O, these streams may be sufficient and easier to use, although potentially less efficient than byte buffers for large data transfers. Asterisk buffered reader / buffered writer asterisk for line-based I/O, these classes offer convenience methods for reading and writing text lines. Asterisk memory mapped files, mapped byte buffer as covered earlier, this is extremely efficient for large file operations where you want to treat the file as memory. Asterisk serialization / deserialization asterisk for complex object structures, consider serialization / deserialization libraries like Jackson or JSON. These libraries can handle the conversion between objects and byte streams, or other formats like JSON. Asterisk protocol buffers, protobuf a language-neutral, platform-neutral extensible mechanism for serializing structured data. Protobuf is very efficient for network communication and data storage. Asterisk Apache Arrow asterisk a language-independent columnar memory format for data analytics. Arrow is designed for efficient data processing and transfer. Conclusion. Byte buffers are a powerful tool for efficient I/O operations in Java. Understanding their types, creation, usage, and best practices allows you to build high-performance applications that can handle large amounts of data effectively. By carefully choosing the appropriate buffer type, managing the position and limit attributes, and handling byte order correctly, you can optimize your I/O code for maximum performance. Remember to consider memory mapping for large file operations and buffer pools for network I/O. Mastering byte buffers is a valuable skill for any Java developer who needs to work with I/O intensively.